Okay, so depending on your experience with algebra in the past, you may or may not have ever heard of the term log function or logarithmic function. So we're going to develop what it is over today's class. And we're going to start with a brief summary about inverse functions. So remember, only one-to-one functions have inverses that are functions. And you can test if the graph of a function is one-to-one by using the horizontal line test. If a function is one-to-one, its inverse function can be found by interchanging x and y in the function's equation and solving for y. The domain of f is the range of f inverse, and the range of f is the domain of f inverse, because inverse functions swap the role of input and output, so domain and range swaps. The graph of f inverse is the reflection of the graph of f over the line y equals x. That is, to get points on the graph of f inverse, you have to reverse the coordinates on f. Because inverse functions undo each other, when you compose two inverse functions, you get x back, right? So f composed with f inverse of x gives you x, and f inverse of f of x gives you x. It's like a round trip. You plug an x in, run it through the two machines, you get the x back. Okay, so remember from last class, an exponential function of the form b to the x is one-to-one, right? So these are the two flavors, exponential growth, exponential decay. Both of them always pass the horizontal line test. Okay, so because these guys are one-to-one, we know that its inverse is also a function. It has an inverse function. So on the graph of 2 to the x here, I'm going to sketch the graph of its inverse, right? Which means I'm just going to reflect this graph over the line y equals x. So I'll put the line y equals x in here as a dashed line, just as a guide. Trying to carefully make it so it's the line y equals x. Okay, so you can either like just picture the reflection over the line y equals x. If you have difficulty with that, you can pick a few key points on the graph, swap their coordinates, and then connect them with a nice smooth line. So let's see, some nice points on this graph would be 0, 1. See, I'll write them on the side here because it's going to get crowded. So x, f of x, right? I've got 0, 1. And then I have 1, 2. This point right here. 2, 4. 3, 8. And then maybe I'll just do like 1 or 2 negative ones. Negative 1, a half. And negative 2. It's really hard to tell on the graph, but we do know the formula. It's 2 to the x. So 2 to the negative 2 is 1/4. So then I'm going to make a little chart where I just swap the input and output. So I'm going to have x, f inverse of x, and I just swap these. So I have 1, 0, 2, 1, 4, 2, 8, 3, 1/2, negative 1, and 1/4, negative 2. And I'll plot those points. 1, 0, 2, 1, 4, 2, 8, 3, and then looks like 1/2, negative 1, and 1/4, negative 2. So now I can use this as a guide, plus the fact that this is supposed to be symmetric over the line y equals x, to try to draw a perfect inverse function. So this is f inverse of x. That's the inverse of 2 to the x. All right, so we can draw the inverse of 2 to the x. Pretty easy. If I want to find a formula for the inverse function, right, you start with the formula f of x equals 2 to the x, interchange the x and the y, so I would have x equals 2 to the y, and then solve for y, right? But how do you undo 2 to something? How would you undo 2 to the y? How do you get y by itself there? Square rooting won't work because that... Yeah, that's what we're learning today. Yeah. We don't have a tool for it. Like, so square root won't work because y could be anything. Y is the variable, right? So y could be 7, in which case you'd have to take the 7th root. But y could also be 25, in which case you'd have to take the 25th root. So you can't take a root of both sides to get that y by itself. You can only do that if the thing in the exponent is a number. It has to be a constant, but y is a variable, it's changing. So we don't have a mathematical way to solve the equation we wrote. We need a way to undo 2 to the y. Yeah, so just go with me. We're just going to name the operation of undoing 2 to the y log base 2 of y. Log base 2 of y. So I'm going to take log base 2 of both sides, right? If I need to undo 2 to the y, we take log base 2 of 2 to the y, and I'm going to take log base 2 of x. So we just invented this random thing. We're calling it a log, right? We just invented it to be the thing that undoes 2 to the y. So log base 2 of 2 to the y is going to be y. And then on the left, we have log base 2 of x. So the equation for the function we sketched is f inverse of x equals log base 2 of x. What? Right? What? I know. I know. It feels so crazy. We just invented something. We needed something to undo 2 to the y, and we said, okay, let's make up a word for the thing that undoes 2 to the y. We'll call it log base 2. Yeah, we didn't make it up. Somebody long past made it up. Okay, so here's the definition of a logarithm, logarithmic function. X has to be positive, b has to be positive, and b can't be 1. We say log base b of x, y equals log base b of x, is equivalent, means the same thing as saying b to the y equals x. Means the same thing. So they're like synonyms. Or it's kind of like, actually, it's exactly like if I said f of 2 equals 4, that gives you the exact same information as f inverse of 4 equals 2, right? Exact same information. These two are the exact same information. You've got 3 pieces of information in each of these sentences, a b, an x, and a y, right? So this one, we're saying, is going to mean the exact same thing as this one. They're just rearranged. All right, we'll do some examples. You'll see it. So the equations log y equals log base b of x and b to the y equals x are different ways of expressing the same thing. Just like saying 10 over x equals 5 and 10 equals 5x are the same, or y equals x and y equals 5x over 5. Those are different ways of expressing the same thing. All right, so I'm going to use this, the definition of a logarithm, to evaluate each of these things, to write each of these equations in its equivalent exponential form. So 2 equals log base 3 of 9. So b in my log equation, we call that the base. That's the base in the exponential equation. So I've got b to the something equals something else. Okay. Sorry, in this case it's a 3, right? My b is a 3. 3 to the 2 equals 9. Yeah, which makes sense. We know that's true, right? So 3 squared equals 9. So you use your base on the logarithm is the base in your exponential. And then you just kind of look at the other two numbers and they change places. because the log function is the inverse of an exponential, so it makes sense that the input of 9 and the output of 2 will change places when you write it in exponential form, because the input and output will switch. All right, let's do another one. So this one says my base is 8, right? And I have to raise 8 to some power and get an answer, right? So which one of the remaining two numbers, -1 or 1/8, is my power? -1, and that equals 1/8. Is that true? Yeah. Okay. All right, so we can go from log form to exponential form. We need to be able to go the other way also. So if 2 cubed equals 8, I want to write this in an equivalent log equation, something of the form y equals log base b of x. So my base is what? 2. Yeah. So log base 2 of what equals what? Okay. What am I taking the log base 2 of? 8. And it equals 3. Yeah. Yeah. So the number that's like 2, that's like the superscript on the 2, the power, is not the number that's right next to the 2 when you switch forms. Just swap them. Okay, so 6 to the -2 equals 1/36. That's true. We all know that's true. So my log equation, equivalent log equation, is going to be log base 6 of something equals something. Yeah, 1/36 goes in here, and the exponent goes over here. It always equals the exponent. All right, so we're going to do some practice evaluating logarithms. We have to figure out what these things equal now, right? We're not just translating an equation we know is true to another form. So log base 10 of 100, we don't know what it is, right? So I could put an x there and say, I don't know what it is. Let's call it x. Now translate this to an exponential equation. And what's my base? 10. What's my exponent? X. And that should equal 100. So what is x? 2. Right? So we would say log base 10 of 100 equals 2. Because 10 squared equals 100. All right, log base 5 of 125. So basically, 5 to what power is going to give me 1/125? -3. So log base 5 of 1/125 is -3, because 5 to the -3 is 1/125. Okay, log base 36 of 6. So 36 to what power equals 6? The 1/2, yeah, because the square root of 36 is 6, and square rooting is the same thing as the 1/2 power. That's starting to feel like, okay, I kind of know what you're talking about. A little bit, okay. Okay, so here are some basic log properties. We're going to try to figure out what these are just knowing the definition. So log base b of b, that's asking you base b, right? To what power gives you b? 1. B to the first is b, right? And I can write a little note under here because b to the first equals b. All right, log base b of 1. So b is the base. To what power that we don't know gives you 1? 0. Because b to the 0 equals 1. All right, log base b of b to the x. What power do you raise b to get b to the x? X, yeah. It's like, what is the name of the boy named George, right? George, yeah. So log base b of b to the x is like x. All right. This one's a little bit trickier, but it's also what is the name of the boy named George? b to the log base b of x. What do you think it is? George, or x? Yeah, it's x. Oh, I should write because b to the x equals b to the x. That's kind of obvious. And this one is because b to the log base b of x. So log base b of x, I'm not going to write down symbols. Let's just think about it in words. If you just were thinking about log base b of x and trying to answer a question that looked like log base b of x, you'd be asking yourself, okay, what power do I raise b to get an x? I don't know, but I'm going to raise b to whatever power you raise b to get an x. It's roundabout again. This is b to the power of b that gives x. Whatever power you have to raise b to get x is log base b of x. So b to that power will always give you x. I can do another argument if the English one isn't working. I'll write it out. B to the log base b of x. Let's see. Okay. So a little aside, we're going to let log base b of x be represented by something simpler for a minute. Let's just call that thing y. Can you guys stop talking in the back, please? Thank you. So I'm going to replace log base b of x with something simpler. Just call it one single letter y. So this is going to be b to the y, right? B to the y. But if log base b of x equals y, change that equation to an exponential form. My base would be b, my exponent would be y, and that will equal x. Done. B to the log base b of x will give you x. Okay. It's okay. It's okay if the justification is a little murky. It's more important that we know how to use these things. So just put it in your box. B to the log base b of x equals x, no matter what b is. Okay, so logs with some special bases. We have the common log, which is log base 10. And we often, when we're using the common log, don't write the 10. We just write log x. And you have to assume that there's a 10 there. So the common log is log base 10 of x, and it means that 10 to the y equals x. And then we have the natural log, because we have the natural exponential function. Its inverse is the natural log. If y equals log base b of x, we shorten that to ln x, which stands for natural log. And you might wonder, why is it ln and not nl for natural log? And my French student, why do you think that it did that? It started out in French, and how do French? You put the adjective before the noun. Yeah. So it was a French mathematician who came up with this. And so you'd say log naturel, right? The natural log. So that's why it's ln, and it's just a fun fact. So if y equals ln x, that means e to the y equals x. So here's a note. These are the only log buttons on your calculator. You have a common log button and you have a natural log button. So if you want to do log of some other base, you have to know some more things about logs. All right, so let's see if we can evaluate each of these logarithms by hand, and we could check them with the calculator. Log of 1,000. So there's no base written there, so you assume it's a 10. So my base is 10. What power do I raise 10 to get 1,000? 3. So log of 1,000 equals 3. Right? And we can check on the calculator because we have a log button. We have a log base 10 button. So the log button is over on the left here. If you have a scientific calculator, that should also be on there. Log of 1,000. Yep, 3. Okay. All right, let's try in our heads to do the log of 0.01. 0.01 is 1 over 100. What power do you raise 10 to get 1 over 100? Negative 2. 10 to the negative 2 is 0.01. Yeah. So we can check log of 0.01 should tell me negative 2. And you can also check by doing 10 to the negative 2, you get 0.01. Okay, the ln of e cubed. 3, yeah. What is the name of the boy named George, right? This is log base e, so my base is e. And so this is asking you, what power do you raise e to make e cubed? 3. And we can check on the calculator. You have an ln button right under your log button. Ln of e cubed gives me 3. All right, how about the ln of 1 over e squared? Close. Negative 2. 1 over e squared is the same thing, oops, as e to the negative 2, right? And so this is there's a little base e here. So I'm asking e to what power gives e to the negative 2? The negative 2 power. And we can check on the calculator, ln of e to the negative 2, negative 2. All right, the ln of 5. This one's trickier. The ln of 5. So my base here is e. So we're trying to figure out what power do you raise e to make 5. So this is saying e to what power equals 5. I don't know. So what is e again? 2.718 is e, yeah, approximately. So 2.718 to what power will give you 5? We'll give you 5. So to the 2.5? All right, let's see. We can try. So we'll try doing e to the 2.5. That's Henry's guess. Too big. Too big. So let's make the exponent a little smaller. What do you want to try next? E to the 0.3? Too small. 2.025. E to the 2.025. That's still a little bit too big. 1.75. Too big. 1.61. Oh, very close to 5. Yeah. So you can't do this one in your head. Right? There's no way I would expect you to know what value to raise e to make 5. That's what the ln button is for. If you wanted to know what value you should raise e to make 5, use the ln button. Right? So x turns out to be approximately 1.6. So if I hit the ln of 5, I get approximately 1.6. Yeah, it's an irrational number. Yeah, that's why I wrote approximately. So the ln of 5, that's the number you raise e to make 5. Okay, so graphs of log functions. We already sketched the graph of log base 2 of x by reflecting the graph of 2 to the x over the line y equals x. These pictures illustrate the relationship between the graph of an exponential function and its inverse, a log function. So this one is for bases greater than 1 when you have exponential growth. Its inverse looks like a really slow growth. Call that a logarithmic growth. And if you have exponential decay, reflect over the line y equals x. This is a log that has a base between 0 and 1, which is not commonly used. Right? This is really the picture you want to have in your head for a logarithmic function. But for both of them, just looking at the red graph in both pictures, what is the domain? No. 0 to infinity. Neither of these graphs crosses the y-axis. They start at 0 and go to infinity for x values, and they don't ever touch 0. It looks like the y-axis is an asymptote. How about the range for both red graphs? Negative infinity to infinity. And are they both 1 to 1? Yep, they have an inverse. We know that because they are the inverse of an exponential. You're lost. I'm just looking at this red graph and this red graph. Yeah. So both of them live on x values from 0 to infinity. They live on y values from negative infinity to infinity. Do either of them have any extrema? No, no maxes and mins. Y-intercepts? None. It never touches the y-axis. It's an asymptote. How about x-intercepts? They both have 1, 0 as an x-intercept. Do they have any asymptotes? Where are they? X equals 0. Vertical line, x equals 0. And end behavior. They have, the two different graphs have different end behavior. So let's write those out separately. We'll say when b is bigger than 1, so that's the first graph. As x approaches infinity, log base b of x approaches, what's happening? Infinity. It is always going up. It's always getting bigger, just very slowly. And as x approaches negative infinity, log base b of x approaches, oh, x can't approach negative infinity, right? Because it doesn't live over there. What's the furthest left my x can approach? 0. So we'll say as x approaches 0 from the right. That might be new notation. But as x, just think of it as x approaches 0, what's happening to the y values? Negative infinity. They're going down. Okay. And then let's do our end behavior for this graph when b is between 0 and 1. As x approaches infinity, log base b of x approaches negative infinity. And then the furthest left my graph can approach is 0. So I'll say as x approaches 0, log base b of x approaches infinity. Good. All right, here's the graph of f of x equals log base 2 of x. We sketched this earlier by doing a reflection of 2 to the x. So we could now use this as a new parent function to sketch transformations. Okay. So if I just put the parent on both of these to help guide us, right? If I wanted to do log base 2 of x plus 3, how would I transform log base 2 of x to get 3 to the left? Yeah. So I can just pick a few nice points on this graph and move each one 3 to the left. And then I've got this point here, go 1, 2, 3 to the left. And this point here, 1, 2, 3 to the left. And then I've got 8, 3, 3 to the left. And 16, 4, 3 to the left. So my new graph is going to, and my asymptote used to be at y equals 0. Now it'll be at, sorry, x equals 0. Asymptote used to be at x equals 0. Now it will be at x equals negative 3. Just move it 3 to the left. So my new graph looks like this. So I just shifted my new parent, and I only know what it looks like because we sketched it earlier by reflecting 2 to the x over the line y equals x. And now I know what that looks like, so I can graph its transformations. All right, so for the next one, if I want to graph negative log base 2 of x, what kind of transformation is that? Or it's a reflection over the x-axis, because that negative is post-operation, outside the log function. So reflect over the x-axis. So that point's going to stay where it is because it's on the x-axis. This point at 2, 1 would go to 2, negative 1. And then 4, 2 will become 4, negative 2. And 8, 3 will become 8, negative 3. 16, 4 will become 16, negative 4. And then maybe I'll do a couple over here, like negative a half, negative 1 will become negative a half, positive 1. And then negative a quarter, sorry, positive a half 1 becomes a half, negative 1. So now I connect these with a nice smooth line. And I get a reflection over the x-axis. So we learned earlier today that the domain of a log function is the set of all positive real numbers, or 0 to infinity, right? We did that just a couple minutes ago. We wrote down the domain of a log function as 0 to infinity. What is the domain of log base 4 of x minus 3? Close. 3 to infinity. So this is going to be the graph of log base 4 of x, which will have this same standard shape. It will look the same and have the same domain as log base 2 of x, because all log base b of x's look generally like this one, right? This was a generic log base b of x, and its domain was 0 to infinity. And now if I'm going to shift this graph, how am I shifting it? 3 to the right, right? So y equals log base 4 of x has an asymptote at x equals 0, right? That's the furthest left you can go, because log base b of any base of x will have an asymptote at x equals 0. But then I'm going to shift this guy 3 to the right. So y equals log base 4 of x minus 3 has an asymptote at x equals 3, right? We shift it 3 to the right. And that's going to shift our whole domain 3 to the right, because it won't pass that asymptote. So instead of being 0 to infinity, my domain will be 3 to infinity. Okay, I'm glad we're here because I can see all of your eyes glazing over. So I have an activity for you where we do some applications of where you might use logarithms.